Right, good afternoon. Today we're going to start with chapter 12. What do you need to do chapter 12? You need to do revision on 6.7, the differential amplifier you did in electronics 2. But today we're going to start with the opamp, and that is chapter 12. The introduction to the operational amplifier. You're going to talk about the operational amplifier, all the characteristics. All right, that's the first lesson. All right. All right, first of all, the symbols. Here's a symbol of an op-amp. When we look at the symbol of the op-amp, we got two inputs, the inverting input and the non-inverting input, and we got output. Now, first of all, what is the meaning of inverting input? What does the inverting input do? If I make that input more positive than my non-inverting input, the output will go where? The output will go negative, all right? Because it inverts, all right? If I make this negative with respect to my non-inverting input, I make it negative, where will the output go? It will go positive. It will always give you a 180 degrees phase shift. Positive will go negative, negative will go positive, all right? That is my inverting input. My non-inverting input, if I make my non-inverting positive respect to my inverting input, I make it positive, my non-inverting input, the output will go positive. There won't be any phase shift. If I make it negative, the output will go negative, all right? Then we got a split supply on the op-amp, a plus V and a minus V. That means we make use of a split supply, positive voltage as well as a negative voltage. Now here I made a drawing, it's not very clear. But if I take two 15-volt batteries, connect them in series, take the one output there, take the center point to that'll be my 0 volts, and that'll be my negative. That means if I put a black lead of a multimeter here, the red lead there on a voltage scale, it will give me plus 15 volts. Black lead there, red lead there will give me minus 15 volts, all right? If I put my black lead here, my red lead there, what will it give me? It will give you 30 volts because they're in series, negative, positive, those voltage will add up. It won't give you 0 volts, it will give you 30 volts. All right. Different op-amp packages. The one you will normally use in the lab is this package here. Start from, you see there's a dot there or there, start from the pin 1 to 4, and then on the other side, 5 to 8, all right. It's an 8-pin IC, all right. The one you're going to use is 741. Any questions? All right, basic op-amp representations. All right, first of all, we're going to look at the ideal op-amp. When I talk about an ideal op-amp, that is the ideal. You won't get an ideal op-amp, but that's the ideal. First of all, we look at the input side. They tell us the input impedance is infinite. That means very high input impedance. That means we're not going to draw any current. That means there's not going to be any current flow between that. It's like two open ends. All right? Then they talk about the voltage gain. AV stands for the voltage gain. Voltage gain is also infinite. That means if I multiply anything by infinite, what will I get? You will get infinite, all right. Very high voltage gain. Output impedance is 0. That means output impedance is 0. That means when I draw any current, there won't be any volt drop inside a device. That means there's 0 output impedance, like a short circuit, all right. You with me? Now we go and look at the practical op-amp. I will have an input impedance, there is Z in, but it's also going to be very high. It will be a very high input impedance. Voltage gain, also going to be high. Output impedance is going to be low. All right. That means the practical op-amp, high input impedance, high voltage gain, and low output impedance. All right, you with me? Any questions on that? Any questions? No questions. All right, let's move on. The basic internal arrangement of an op-amp. What is inside an op-amp? First of all, I've mentioned to you 6.7, the differential amplifier, all right? The input stage of the op-amp is a differential amplifier, all right? Then we talk about a voltage amplifier gain stage. That will be like a common emitter amplifier, small signal amplifier. And then on the output, you will have a push-pull amplifier to deliver a little bit more current, all right? First of all, I repeat, differential amplifier, a voltage amplifier gain stage, and then a push-pull amplifier. Any questions? All right, this was also done previously in 6.7. You also look at single-ended differential mode. When I talk about a single-ended differential mode, my one input is connected to my reference, 0 volts, and I got one input here. You see, here is my input. Output will be 180 degrees out of phase. Why? Because I'm putting my input at my inverting input. All right, 180 degrees phase shift. In this case, my inverting input is my reference, and I apply my signal at my non-inverting input. That means this signal and the output signal will be in phase. All right, there won't be any phase shift. All right, then we're going to look at double-ended differential mode. Double-ended differential mode. You can see these two signals are going to be 180 degrees out of phase. All right. I can do it that way, or I can do it that way. It will give me exactly the same. All right. But you can see those signals are 180 degrees out of phase. Then we'll come to I think the most important one. Common mode operation. Now, if we look at common mode operation, you can see these two signals are exactly the same. Both the input signals are exactly the same. What is my output? 0. Now, what is the use? Applying two signals and get 0 out. What? The? Now, why can we use this? Because I apply two signals and I get 0 out.
It is used to prevent an unwanted signal.
All right. Normally, we got noise in the air and we don't want to amplify noise. Now, when we're going to look at common mode rejection ratio, that's the ability to get rid of the noise. All right. Because your noise signals could look exactly the same, that means if this noise signal is coming on both the inputs, what will happen? It will cancel out, all right? And we don't want to amplify the noise, all right? And that brings us to common mode rejection. That will be the next thing we're going to talk about. All right, yes, common mode rejection ratio. If I look at the common mode rejection ratio, I talk about AOL. AOL stands for open loop gain. That means when you don't have any feedback on your amplifier. That is my open loop gain. ACM is my common mode gain. The open loop gain will normally be very high. It will be in the region, if I talk about a 7-for-1 op-amp, it will be in the region of 200,000. That means 200,000 is quite a large gain or high gain. My common mode gain is normally very small, in the region of 0.2 or 0.1 or what the case may be, all right? And then we can also express it in dBs, 20 log open loop gain divided by my common mode gain. You see here they talk about an open loop gain of around about 200,000, and that is the ability to get rid of the noise, all right? Let's have a look at the example to basically illustrate. We look at example 12.1. They say a certain op-amp has an open loop differential gain of 100,000. That is my open loop gain. And a common mode gain of 0.2. You can see the common mode gain is quite small. Then they say determine the common mode rejection ratio and expressed it in decibels. Common mode rejection ratio, open loop gain divided by the common mode gain is 100,000 divided by 0.2. It will give me 500,000. All right. When I express it in dBs, it's 20 log of 500,000 will give me 114 dBs. All right. You can see your common mode rejection ratio is quite high. All right. The next thing, maximum output voltage swing, V out peak to peak. Now, quite important, what determines the maximum output of an op-amp? What determines the maximum output of an op-amp? Anybody? The input. What are you saying? Tired? What determines the maximum output of an op-amp? The input.
Yes.
Yes, sir. Wrong, sir. The maximum output will be determined by the supply. That means the supply voltage will determine your maximum output. All right. Let's say, for example, I got a certain input, I got a certain gain. The output should go to 100 volts, all right? But my supply is only plus 15, minus 15. It can only go to 15 maximum, all right? Also dependent on the load, all right? You with me? That means the maximum output of an op-amp will also always be determined by the supply. All right, let's have a look. They give us here values. Now they say a Fairchild KA741. Fairchild is the manufacturer of the device. It's a 741 op-amp. They say the supply voltage was given as plus 15 minus 15 volts. All right. Supply plus 15 minus 15. All right. Then they say if I got a load of 2 kilo ohms, the load is 2 kilo ohms, and I want the device to saturate, it will go to plus 13 minus 13 volts. All right. Why? Because we got output impedance, and when there's current flow, what happens? Due to the current flow, there's a volt drop inside the device. All right. The larger the current, the larger the volt drop inside the device. Then they go to a value of 10K. They make that load resistance 10K. And now the output voltage increased to plus minus 14 volts. All right. That means with a higher load or larger load resistance, the current is smaller, the volt drop in the device is also smaller. All right, you with me? That means, I repeat, maximum output is always determined by my supply. Any questions? No questions? All right, next part, input offset voltage. Now, if I apply 0 volts to the input of an op-amp, what should the output be?
0.
The output should also be 0, all right? But now we find that is not the case. Because what is the input stage of an op-amp? A differential amplifier. And what do we have in a differential amplifier? We got transistors, right? Now that base emitter junctions is normally, they try to manufacture them identical, but sometimes there's a small mismatch there. That means it's not going to be exactly identical. And that will give us offset voltage. They state the ideal op-amp produces 0 volts out for 0 volts in. In practical op-amp, however, a small DC voltage, V out error, appears at the output with no differential input voltage is applied. Its primary cause is a slight mismatch of the base emitter voltages of the differential amplifier input stage of the op-amp. As specified in op-amp datasheet, the input offset voltage, VOS, is a differential DC voltage required between the inputs to force the output to 0 volts. Typical values of input offset voltage are in the range of 2 millivolts or less. In the ideal case, it is 0 volts. Input offset voltage drift is a parameter related to VOS that specify how much change occurs in the input offset voltage for each degree change in temperature. Typical values range anywhere from 5 volts per degree Celsius to about 50 microvolts per degree Celsius. Usually an op-amp with higher nominal value of input offset voltage exhibits a higher drift. All right. That means we don't want it, but it exists. All right. And that is due to the base emitter voltage mismatch. All right. Now we're going to look at the input bias current. All right, the input bias current, because we will have currents flow there because we got a transistor, and when we want to switch these transistors, we need a bias current to switch them, all right? And my input bias current, we get the average of those two currents, all right? That will give me my input bias current. My input impedance can be specified in two different ways. They can specify the input impedance in the differential input impedance, then it's like that, or the common mode input impedance, then it's going to be like that. All right. Differential or common mode. You should know the difference between differential input impedance and common mode input impedance. All right, input offset current. What should I say about I1 and I2? They should be equal. Now, if they equal and I subtract them from one another, what should I get? I should get 0. All right. That is the ideal case. It should be 0, but it isn't 0. All right. We just work with the absolute values, but it isn't 0. And due to that small difference in current, I will get a certain error output voltage, all right? And all right, let's have a look what they did here. They say VOS is equal to I1 times Rin, that vol drop, minus that vol drop. Because the resistance are exactly the same, I can say it's I1 minus I2 times Rin. Then I can say VOS is equal to IOS times Rin. But the output error voltage, let me just move it a little bit upwards. The output error voltage will be the voltage gain times that VOS. And VOS is IOS times Rin. That will give me my output error voltage, all right? And then they say, how do they specify? They say change in offset current with temperature affects the error voltage. Values of temperature coefficient for offset current in the range of 0.5 nanoamps per degree Celsius are common. All right, just give us what's a common value for that. We already talked about the output impedance. There you can see the output impedance. That means the moment I draw more current, the larger current I draw, the larger volt drop will develop inside the device. All right. Smaller current, less volt drop inside the device. All right. Everybody with me? Now we're going to talk about slew rate. What is slew rate and how do we determine the slew rate? All right, slew rate. First of all, they talk about a test circuit. Now, we look at this circuit here. What do you think? Is there any feedback in the circuit, yes or no? Positive feedback or negative feedback? It's negative feedback. Why? Because we take from the output to my inverting input, all right? And there's a 180 degrees phase shift. That's why it's negative feedback. If I take this wire from there to that position there, then I will have positive feedback. And when you got positive feedback, the device will saturate, all right? That's why to decrease my gain, I will always apply negative feedback. This test circuit is known as a voltage follower, all right? When I talk about a voltage follower, it will follow the input voltage. That means the input voltage will always follow that input voltage, all right? But now, what do? We apply a step input function. That means this output should look like that. Not like the blue line, it should look like that, all right? But now it takes a certain time for the output of that op-amp to change state from maximum negative to maximum positive, right? It'll take a certain time. And that's what we're going to do there. And how do we do it? You can see here, from negative to positive, it takes a certain time. That's why they talk about delta T, the change in time. We also going to look at the change in voltage. And then they say slew rate is delta V out divided by delta T. The change in output voltage divided by the change in time. Now, best to illustrate that, let's have a look at the example. Example 12.2. Example 12.2. They state the input voltage of a certain op-amp appears as shown in figure 12.12, sorry, in response to a step input. Determine the slew rate. Now, on your oscilloscopes, sorry, previously, we had 0% and 100% on the screen. Now, if you want to determine the rise time of any pulse or the fall time of any pulse, you will put it between the 0% and the 100%, all right? And then you will work to 10% and 90%, and then you will determine that time. That will be the time, the rise time of the pulse, all right? Same with the fall time. You will go from 90% to 10% to determine the fall time. Now, here you can see this thing goes from minus 10 to plus 10, all right? But that's why we go 10% up and we go 10% down, all right? And from there to there, that is my time, 1 microsecond, all right? And the voltage vary from plus 9 to minus 9, or minus 9 to plus 9. That means plus 9 minus minus 9. That means a minus times a minus will give me a positive. That means that will give me a total of 18 volts, all right? The change in voltage is 18 volts. The change in time is 1 microsecond. That means 18 volts divided by 1 microsecond. It will be 18 volts per microsecond. That is my slew rate. But that will normally be supplied by the manufacturer. That means you want the slew rate of that device, you can go to the data sheet, or today you go to the internet, and then you can find all that information about that device. All right. Any questions? Yeah.
So, meaning it will always be 10%. It cannot be, maybe be, or it doesn't depend on the rise time. It has to be a straight line.
Yeah, you see, you normally get something like that, all right? It's normally not straight like that, you understand? And that's why they go 10% up and 10% down to get on that slope, on that straight slope, all right? Because how do you determine, that position's there? That's why they normally go 10% and 10%. From the top, 10% down, and from the bottom, 10% up, all right? Or let's say from 10% to 90%. That's a standard. Next part of our work, frequency response. All right. Chapter 10. Do you know chapter 10? Yes, sir. We know chapter 10. That means now I can ask a few questions on chapter 10. Is right? If you think about a common emitter amplifier, why does it cut off on the low frequency side? Why does it cut off on the low frequency side? Anybody? Please, anybody? Hey, a long time ago. That means I must send you back to electronics too. No. I will send you back to Mr. Gous. He would like to see you again. All right, nobody. All right, we got bypass and coupling capacitors, right? You got bypass and coupling capacitors. Now, at low frequencies, what can I say about my capacitive reactance? Will it be high or will it be low? Your capacitive reactance will be high. What is capacitive reactance? It's basically your AC resistance of the capacitor, all right? It's going to be high. When I got high resistance, what can I say about the volt drop? It's going to be large. That means a lot of the voltage is going to be dropped across those capacitors. And that's why the amplifier don't function nicely, all right? Now the frequency increase, and now it's amplifying nicely, constant. And then when I go higher and higher, it starts drop off on the high frequency side. Why does it drop off on the high frequency side? Anybody? Why does it drop off on the high frequency side? Huh? No. No, that was on the low frequency, not on the high. I said to the low frequency was the coupling and the bypass capacitors. Why does it cut off on the high frequency side? Internal? All right. Junction capacitance. Inside a transistor, we got junctions. There's N and P material. It forms a layer, and it will have a small amount of capacitance. But when I go to a high frequency, that capacitive reactance decrease, and it actually creates short circuit inside the transistor. Then the transistor don't function anymore, all right? And that's why it cut off on the high frequency side. Old news, eh? All right. Now, here we're going to look at the frequency response of an op-amp. Now, an op-amp don't have coupling and bypass capacitors. And an op-amp has no internal coupling capacitors, right? That means, what can I say about low frequencies? Will it amplify low frequencies, yes or no? No. No, yes. It will amplify low frequencies. It will amplify DC. All right? You with me? Can an op-amp amplify low frequencies? All right. Because there's no coupling capacitors, it can, I say, an op-amp has no internal coupling capacitors. However, therefore, the low frequency response extends down to DC, 0 hertz. That means DC don't have any frequency. It's a straight line. That means it can amplify DC. All right. On the high frequency side, it will cut off. Why? Because we got junction capacitance of my transistors inside the device. That means on the high frequency side, it will cut off due to my transistors. You with me? Any questions? All right, let's move on. I want to look at this comparison between different op-amps. I'm not going to look at all of them. I will take the one we're going to use, and I will take the best, or the op-amp with the best characteristics, the op-amp closest to the ideal device. All right, the one you're going to use in the lab, LM741. Common mode rejection ratio in dBs, they give you a minimum value of 70 dBs. Open loop gain, typical value, 200,000, all right. That means it can amplify 200,000, open loop. Input offset voltage, millivolts maximum, 6 millivolts maximum. Input bias current in nanoamps maximum, 500 millivolts. Input bias current 500 nanoamps. Input impedance megohm, a minimum value of 0.3 megohm. That's minimum, it can be more. Slew rate, a typical value, 0.5 volt per microsecond. And then the Where do they use it? Industry standard. That means in industry, they can use it a lot. All right. Then we're going to look at the OP177. Common mode rejection ratio, 103 dBs minimum. That was 70, this is 130, basically double. Open loop gain, typical value, 12 million. That means that device is going to amplify the signal 12 million times. All right, that's without any feedback. Input offset voltage in millivolts, the maximum value, 0.01 millivolts maximum. Input bias current, 1.5 nanoamps instead of 500 nanoamps, all right? Maximum value. The input impedance, there we had a minimum value of 0.3 megohm. Here we got a minimum value of 26 megohms. Now 26 megohms is a fairly high resistance. Slew rate, there it was 0.5 volts per microsecond. Here we got 0.3 volts per microsecond. And they say it's an ultra precision op-amp. The big difference between these two will be the following. For the one, you're going to pay much more than the other one. It's like motor cars. You can buy a cheap car and you can buy a very expensive car. But it's not, both of them will work, but depending on the applications where you will use it, all right? This OP177, you will use it for specific applications. Any questions? Yes.
So here, the LM741C, the open loop gain is 106.
It's in dB. If you go and convert it, you will get its value also equal to 200,000. It's just expressed in dBs, all right?
So is it necessary to know maybe for LM7147 the common mode rejections and the open loop gains?
No, that will be quite unfair to know all those things. That means if I want you to do certain things, I will give you the information, all right? You don't have to know it. I know it because I repeat it a lot of times, all right? That's why I can tell you 7 for 1 open loop gain is 200,000 and things like that. But you don't have to learn it off by heart. We will normally supply with you. If I want a question, a data sheet question, I will give you the information and then I'll ask you questions from that. All right. All right, the next part of the work, I'm not going to go on with this because the other class, we're not there. The next part of the work next time, that'll be Monday. We will start looking at negative feedback. All right, what I want you to do, to go and revise negative feedback, revise 12.3, 12.4, and 12.5 for the next class. That'll be on Monday. All right. Any other questions? All right, then there's no questions. All right. See you on Monday.